Welcome to this video prepared by EPB Standards Experts, which demonstrates the use of the spreadsheet which is supporting the simplified case study on EN ISO 52000-1, which concentrates on the demonstration of the delivered and exported energy weighting. First, let's have a quick overview of the contents of this video and of this spreadsheet. As usual, the first two sheets are just information about this spreadsheet. The info sheet is administrative information about the author, about the purpose, limitation, responsibility, a disclaimer, terms of use and background information about this sheet. The explanation sheet gives you general information about how to use each sheet. For example, the fact that all the values you may change are on a yellow background. And sometimes you may change value with these arrows, or you might check a box to decide if some value is true or false, or 1 or 0, as we will see. Anyway, this is always on a yellow background, where you may change data. Generally, the green is used for renewable primary energy, red for non-renewable primary energy, and other colors for the other weighting types. Here you have a list of the main feature and a list of the sheets that we will go through one by one. Please always remember that this spreadsheet is intended to demonstrate specific features, so it is just one calculation for one time interval with the exception of the sheet about matching factor. Here are the links to EPB Center website when you can get more information. Let's start with a simple example. Set of a building that just requires some heat. This heat is produced by a boiler, but it can be assisted by a thermal solar system. The area on top of the sheet shows the graph with the path of the delivered energy carriers. So we have thermal solar, gas and electricity from the grid. The value of the heat required, of the auxiliary energy required by the technical system and of the thermal solar contribution can be changed by acting on these buttons. When you update these amounts, the table here is automatically updated. The first table is just a list of the delivered energy carriers where you can find the amount, the weighting factor as non-renewable primary energy and as renewable primary energy, and then the associated primary energy, as well as a renewable energy ratio for the total. The second table will be used when we will deal with exported energy. In this simple case, there is no exported energy, so we are just going through the basics of weighting delivered energy. In this last table, you can change also the primary energy factors for each energy carrier. On all this sheet, you will find additional information such as the intended use of this sheet, and on the right there are also additional explanation on what you can do by acting on the selection arrows. The area below the sheet is just the input data for the controls and the calculation of the value to be displayed, so nothing to be touched. Let's start with the simple condition that all the heat is produced by the boiler without any assistance by the thermal system. In this case, the only two energy carriers are electricity, grid electricity and gas, and you just sum up the corresponding primary energy for each of the two energy carriers and you get the result in these rows. Of course, the renewable energy ratio is quite low because there is just a small contribution of renewable energy by the grid electricity. Since there is no exported energy, if you change the value of K exported between 0 and 1, no change appears on the energy performance of the building. Now, if we add some contribution by the thermal solar system, of course the contribution of the boiler reduces, and since we are replacing a contribution by a fossil fuel by thermal solar, the renewable energy ratio increases when you increase the thermal solar contributions. Using thermal solar is not the only way to have renewable energy in this example. Let's set to 0 the contribution by the thermal solar. We can replace the natural gas energy carrier by biogas. This means that we have to update the weighting factor for the gas. For biogas, it might be 0.2 for the non-renewable primary energy factor and 1 for the renewable primary energy factor. With this setting, now the renewable energy ratio is 0.72 because there is a much larger contribution of renewable energy by the biogas. This shows clearly that the property renewable, non-renewable is a property of the energy carrier, not of the device. A boiler can be more or less efficient, but still a boiler can use both fossil fuel or biofuel, resulting in a different use of renewable energy. Now let's introduce exported energy with a simple example about PV. This is a system that requires only electricity that can be provided by the grid or by an on-site PV panel. The starting point is a condition where all the electricity is provided by the grid. The 100 kilowatt hours that are required by the building are all provided by the grid. Please note that the first table now includes also the possibility of having exported energy. In this table, this exported energy will be evaluated according to the resources needed to produce it on site. So it will be evaluated with the same weighting factors as the corresponding delivered energy, which is PV electricity. The second table is not yet relevant because there is actually no exported energy until now. Even if I change the K exported from 0 to 1 or 1 to 0, nothing changes in the energy performance. Now let's increase the PV production. As soon as the PV production is increased, the contribution by the grid is decreasing, and the renewable energy factor is increasing because grid electricity is replaced by PV electricity, up to the point where the PV production is providing exactly the electricity required by the building and no more electricity is taken by the grid. In this condition, obviously the renewable energy factor is 1. Until now, there is no effect of the choice about K exported because there is no exported electricity. As soon as the on-site PV electricity production exceeds the needs by the building, then exported electricity appears. As it was explained in the video about exported electricity, if the K exported is set to 0, in this case, the exported electricity is evaluated according to the resources which were used to provide it. That is the cost of PV electricity production. In this case, the energy performance is unchanged by the amount of exported energy. However, energy available externally appears because this exported electricity has not been taken into account in the energy performance of the building. So it's correct to know that this is available for use externally and its cost was to produce it with a PV panel. So it is qualified as renewable electricity with the same conversion factor as PV. This is a relevant information, for example, if this contribution is taken into account in an energy community. If we decide to select K exported equal 1, in that case, the exported electricity will be evaluated according to the avoided use of resources by the grid generator. So in this case, to complete the calculation, we have to take into account again the cost of producing the exported electricity, that is 30 kilowatt hours of PV electricity, and we deduct the resources avoided by grid generators. So we get the resulting energy performance after taking into account the exported electricity. And the result for non-renewable primary energy is a negative value. And the renewable energy ratio is higher than 1 because we have produced more than what is needed inside the building. In this case, we have already taken into account the exported electricity into the energy performance of the building, which is now affected by the amount of exported electricity. So the energy available externally will be set to 0 because we have already taken into account the effect of exported energy into the energy performance of this building. So it's not fair to take it into account a second time outside the building. This would result into double counting. Please observe the behavior of the renewable energy ratio if we further increase the electricity production on site. First of all, the renewable energy ratio will increase a lot up to very high value like 10.33, and then it will turn to negative if the total primary energy will be negative as well. This is not a contradiction, this has a physical meaning. It means that the more energy we produce, the more we save. Also, the negative value of the non-renewable primary energy has a physical meaning. It means that the existence of this building reduces the amount of non-renewable primary energy used by the world, because we assume that the non-renewable primary energy that would have been used has been replaced by the PV production of this building. The next sheet is about a heat pump which can be powered either by the grid or by an on-site PV panel. The diagram allows to play a little bit more with energy flows. You start from a heating need and you might apply an emission and distribution efficiency that will change the heat required to the heat pump. Let's assume 100% to simplify the numbers. Then you take into account a COP of the heat pump, and this results in electricity which is required by the heat pump. In this case, 2000 kilowatt hours divided by 4 is 500 kilowatt hours, which are provided now entirely by the grid. Then there is an additional energy flow which is heat captured from the environment. This case is quite similar to the previous one. The difference is the presence of this energy flow captured from the environment that by regulation has to be considered as renewable energy use. Even using only grid electricity and assuming a COP of 3.5, then the renewable energy ratio is still higher than 0.5 because there is this amount of renewable energy captured from the environment. Of course, if the COP increases, then the renewable energy ratio increases as well because there is less electricity compared to the heat captured from the environment. And of course, if PV electricity is used, then the renewable energy factor will increase and of course reach 1 with K exported equal 0. And just like in the previous example, if the PV production, the on-site PV production is exceeding the needs, then if the K exported is set to 1, the non-renewable primary energy can result negative and the renewable energy ratio can be higher than 1 and again turn into negative values for very high PV contribution. Now let's bring back to 0 the PV on-site production so that we can easily compare the situation with the next sheet, which is the situation where we have a chiller instead of a heat pump. The cooling need is the same, 2000 kilowatt hours. We neglect here the emission and distribution efficiency, and our chiller has to extract from the building 2000 kilowatt hours. With an EER of 4, that means that we need 500 kilowatt hours electricity, just like in this case, but then the electricity adds up to the extracted heat and the sum will be the rejected heat towards the environment. Until now, the rejected heat was not considered as part of the delivered or exported energy. So the renewable energy ratio in the case of the chiller is quite low if we are just using grid electricity, and grid electricity is mainly non-renewable. Of course, if the chiller is running thanks to the PV electricity, in this case the renewable energy ratio can be 1 or even higher if we set K exported equal 1. There is ongoing work about whether to consider or not rejected heat into the energy performance of the building. With the current default values of EN ISO 52000-1, this is not considered. The next example is about a boiler with PV panels. The diagram lets you take into account an efficiency of your heating system. So the heating need here is 1000 kilowatt hours, and with the heating system thermal efficiency of 80%, you need 1250 kilowatt hours of gas as an input of the boiler, plus some auxiliary electricity input. That's what is represented in this diagram. The auxiliary energy can be supplied by the grid or by the PV panels. If there is no contribution by the PV panels, then the system is quite simple and we are just summing amounts of delivered energy. Now, if we increase the contribution of the PV panels, if we increase the contribution of the PV panels, they will contribute to the auxiliary first. If the K exported is set to 0, even if the on-site production of electricity exceeds the required electricity input for the auxiliary energy, then this will be discarded from the energy performance of the building. And no matter how much PV electricity we are generating on site, the system will be shown as running mainly on natural gas, that is fossil fuel, and the renewable energy ratio will be always low. You can only compensate auxiliary energy needs with your on-site PV panels. But if we select K exported equal 1, then the exported electricity will be taken into account in the energy performance of the building. And if you have enough PV production, you can even overcompensate the use of natural gas and get an energy performance in terms of non-renewable primary energy which is negative. Or even you could even have a negative renewable energy ratio if your total primary energy becomes negative. This clearly shows that when K exported is selected as 1, there can be a cross-compensation between energy carriers. That means that the export of one energy carrier can compensate for the delivery of another energy carrier. And the use of fossil fuel can be compensated by the export of on-site renewable energy production. This is not possible if you select K exported equals 0, because the exported energy will not be taken into account into the energy performance of your building. But energy available externally will appear as a secondary result of the energy performance calculation. The next example is about the parallel of a boiler and a cogeneration device. This scheme allows a lot of options. You start from a heat use of the building that you can adjust, an electricity use typically for auxiliary energy, and then you define your generation systems. First, you have to decide how much of the heat is provided by the cogenerator or the boiler. In this condition, it's 0% by the cogenerator. That means that the 500 kWh thermal energy is provided by your boiler. Here you can decide the efficiency of your boiler. This results into the amount of natural gas which you require through the assessment boundary. Then you can increase the share of heat produced by the cogenerator. For example, let's say 50%. That means that 250 kWh are now provided by the boiler and 250 kWh are now provided by the cogenerator. For the cogenerator, you have to specify which is the total efficiency, that is thermal plus electrical, and the electrical efficiency. So we know which will be the output as electricity from the cogenerator and the required input as fuel for the cogenerator. Here you see a question mark because you can specify which is the primary energy conversion factors for the fuel for your cogenerator. In this case, 1.10 and 0 is a typical case for natural gas. So we are assuming that our cogenerator is working on natural gas. And then the electricity produced will be partly used in your building and partly exported. For this case, the cogenerator is producing an excess electricity, so 109 kWh are exported. When there is a cogenerator, the first step is allocating the energy input of the cogenerator to the electricity and heat produced by the cogenerator. This is called allocation, and there are several methods. This sheet uses the power bonus method. This area includes all the data for the calculation and the results. This method requires a reference value, which is a grid efficiency. Then, using the electric efficiency and thermal efficiency of the cogenerator, you get the allocation factors for electricity and for heat. That is, the fraction of the incoming weighted energy which is allocated to electricity and to heat. You can see here that only 20% of the incoming weighted energy is allocated to heat. In fact, the power bonus method is very much sensitive to the electric efficiency of the cogenerator. If the electric efficiency of the cogenerator exceeds the grid efficiency, the allocation factors for heat becomes even negative. And you can see this also in the resulting equivalent conversion factor for heat and electricity produced by the cogenerator. Since we use the power bonus method, the equivalent conversion factor for the electricity produced by the cogenerator is the same as grid electricity. And since the allocation factor is negative for heat, you see that we have negative weighting factors for the heat produced by the cogenerator. Other allocation methods do not provide negative value in any case. For more information about allocation method, see EN 15316-4-5, which is dedicated to cogeneration. Now let's isolate the cogenerator to make things more clear. So we assume that the cogenerator is providing the whole amount of heat required by the building, so that we have no influence coming from the boiler. The electricity produced cannot be used inside the building, so a lot is being exported. Let's see what happens now. If we consider K exported equals 0, the exported electricity has no effect on the energy performance. The result is that the system turns out to be really efficient because only 97 kWh non-renewable primary energy has been allocated to the production of heat, whilst we obtain 500 kWh heat and plus some electricity. However, the renewable energy ratio is still 0. There is no renewable energy used in the system because the fuel as the input of the cogenerator is totally non-renewable. There is also a lot of electricity available for use outside of the building. If we set K exported equal 1, then the energy performance is worst in terms of non-renewable primary energy. It raises from 97 to 322, and even negative for non-renewable primary energy. This is happening because the cogenerator is not using renewable energy, whilst the grid electricity had some contents of renewable energy indeed. Things change dramatically if we assume that the cogenerator is fed by biogas. Just trying to replace 0.2 and 1 as conversion factor for biogas, then the energy performance is greatly improved, and there is also use of renewable energy. Again, the fact that renewable energy is used or not doesn't depend mainly on the machine, it's still a cogenerator, but on the type of energy carrier which is used to drive the generator. The next sheet introduces two more concepts, the district heating and the matching factor. This sample building needs electricity and heat. The electricity can be provided by the grid, as shown now, or by an on-site PV panel. The heat can be provided by the boiler using gas or by district heating. You can specify independently how much heat is provided by natural gas and by the district heating. As shown, there is no exported energy because there is no on-site electricity generation. Now let's increase the on-site electricity generation up to the point that it fulfills all the electricity used. Until now, everything simple, this is just delivered electricity. Now assume that due to time mismatch, part of the electricity is not usable directly on site. Let's see, 80% only matches the time when it is required. If K exported is set to 0, the time mismatch causes a reduction of the renewable energy which is used on site. And you can see the result because the performance is getting worse and worse. Now, if we set K exported equal 1, you can see that the matching factor will have no influence on the final result on the energy performance. Because with K exported equal 1, the exported energy is evaluated according to the energy avoided by the grid generators, and when importing, it is evaluated as the energy required by grid generator, so these two terms cancel each other. This means that using K exported equal 1 allows the compensation between on-site energy production at a time and on-site energy use at a different time. The temporary export and import to the grid does not have any effect on the energy performance of the building. This is true only if the conversion factors are not time dependent. If the weighting factors are time dependent, then the export and re-import at different time can have an effect on the energy performance of the building. Also, once again, we can show that the fact that K exported equal 1 allows cross-compensation between different energy carriers. As you can see, if we increase the on-site electricity production, this is compensating the weighted energy related to natural gas and district heating. The same concept is shown again in the next sheet, which is about a heat pump which can be driven either by the grid electricity or by on-site PV panels. Here the diagram starts from the heating need. An emission distribution efficiency is applied to determine which is the amount of heat required to the heat pump. Because of the matching factor, only part of the on-site electricity is used directly by the heat pump. Most of the on-site electricity is exported to the grid. Therefore, the energy performance, if K exported equals 0, takes into account only the on-site produced electricity which is used at the right time. If we set K exported equal 1, all the electricity is taken into account, irrespective of the matching factor. Even if the matching factor is changed even to 0, the energy performance doesn't change. And again, this is true only if the weighting factors are time independent. The next sheet will illustrate which is the reason for the matching factor and its possible order of magnitude. This sheet is different in that the graph is representative the result of the calculation for 24 hours in a typical day. The calculation is shown below the graph. For each one of the 24 hours there is a PV production, there is an energy use, and there is a PV used, which is a minimum of the two. And only the total is shown on the graph on the top. This is shown indeed by this graph, where for each hour there is a bar, a green bar for the PV production, and a red bar for the electricity use. The calculated matching factor is shown in this box. To allow you to experiment with different situations, you might select the total electricity generated by the PV panels along one day. As you can see, the scale is changed in the graph, and this is the total amount during the day, and the distribution is still the same. And for electricity use, it is the same. Here you can control the total amount of electricity which is used during the day, but you can also select a number of typical profile. This profile is for lighting only, so some light is used in the morning, in the evening, and probably in the middle of the day for dark rooms. Then you have also a profile for heating and domestic hot water, so you have a basic heating load plus domestic hot water reload because of a storage, which happens typically early in the morning and late in the evening. Another profile is domestic hot water only, which shows clearly the peaks for the reload of the storage. And the last is a cooling and domestic hot water profile. For each of them you may experiment changing the profile or changing the total amount of produced electricity or used electricity, and show the effect on the matching factor. For example, on electricity, even if the production is much increased, the matching factor is not increasing that much. At some point, even if you increase the electricity produced, the matching factor is stable. That's because there is no more hour where there can be an improvement. Of course, the energy performance would be tremendously affected by the selection of K exported. If K exported is set to 0, in this case, no negative value of the energy performance is possible. As you can see, we get negative values if we allow to take into account all the exported energy. If K exported equals 0, no negative value is possible. If we go for example, domestic and hot water and heating, the matching factor is a little bit improved. And if we put more realistic values for the daily electricity use and the production of 3 kilowatts during winter, again, the matching factor goes down because most of the electricity is required for the heat pump during the night when there is no PV production. What can be shown also is that the matching factor is tremendously dependent on the pattern, and the values are varying a lot. They cannot be effectively predicted by simple correlations, and the best way to do this is going through an hourly calculation. The next sheet is about free cooling. Free cooling means that there is a source which is at a lower temperature than the object to be cooled. This can be taken into account by an additional energy flow through the assessment boundary, whose weighting factor for primary energy will be 0 non-renewable and 1 renewable typically. And you take into account separately the auxiliary energy that might be requested to facilitate the spontaneous heat exchange between the cold source and your building. A possible example of free cooling is using a borehole heat exchanger directly to circulate cold water across the coils of the ventilation system or into the embedded panels in the building. In summer, the temperature of this water will be lower than the indoor temperature in the house, resulting in free cooling. This model allows to specify a cooling need, an emission distribution efficiency, to set the amount of auxiliary energy, and then, as usual, to select how much electricity is produced by on-site PV panels. The calculation is straightforward and results into a high renewable energy rate if few auxiliary energy is required. If PV electricity is added and K exported equal 1, then the energy performance can be greatly improved. The next sheet is basically the same, but in this case it is for free heating. Free heating is probably less common than free cooling, but it might happen again if you have a borehole heat exchanger or any other exchanger in contact with the ground in winter, and you can circulate this water directly through a preheating coil in your ventilation system. The last sheet, multi-weight, is an example of the different possible types of weighting. The example is about a house which is heated by a heat pump, and the heat pump can be driven by grid electricity or by PV electricity. The available controls allows you to define the heating need, the efficiency of the emission and distribution systems, so that you determine the required output to the heat pump. Then you can set up the COP of the heat pump and then the contribution of PV panels. In this table you can define the weighting factors for both non-renewable primary energy, the cost and the CO2 emission for each energy carrier. You may also specify a different weighting factor for the electricity which is imported from the grid and exported to the grid. This might be more or less relevant according to the type of weighting. For non-renewable primary energy, probably you will use the same value. But for the cost, for example, there could be a different price for the electricity that you buy from the grid and for the electricity that you sell to the grid. The choice between K exported equals 0 or K exported equal 1 may apply to any type of weighting, and it is not necessary that it is the same choice for all the types of weighting. Let's start with no contribution from the PV panels. The whole calculation is presented for only one weighting factor at a time. For example, here the first type is primary energy. Actually, we should be a little bit more specific and specify that it is non-renewable primary energy, and an independent calculation should be performed for total primary energy and or renewable primary energy. As usual, if we increase the contribution by the PV panels, the energy performance improves and gets even negative unless K export is set equal to 0. Let's start again from 0 contribution by the PV panels and switch to cost. And obviously the initial cost in euros is 89 euros, and if the contribution by PV panels apply, then the cost goes down to 0. There is no benefit because K exported equals 0 is selected. K exported equals 0 means that the exported electricity is weighted with the cost of producing it, which is 0, so no profit. But if we include the profit of selling electricity, the balance will be negative. This means that we are earning money by selling the electricity to the grid. By the way, we use a reduced cost for the electricity exported to the grid, but of course, if we update this value and increase it, the benefit increases. Cost evaluation is an example of weighting where the time dependency and the difference between import and export are relevant. The last type of weighting that you can try on this sheet is CO2 emission. A negative value of CO2 emission because of PV contribution means that the CO2 emission of the world is reduced by the electricity injected into the network that avoids producing CO2 in generating the same amount of electricity. For more information, please visit the EPB Center website. You will find information on all EPB standard modules and case studies on the main standards. This video has been prepared by EPB Center team in the context of a contract with the European Union represented by the European Commission. The information and views set out in this video are those of the authors and do not necessarily reflect the official opinion of the European Union. Neither the European Union institutions and bodies nor any person acting on their behalf may be held responsible for the use which may be made of the information contained therein.